Hello everyone, welcome back. This is part 10. This is the last part of chapter 13 where we're talking about solutions. And we've been talking specifically about colligative properties. And so in this last part, we're going to talk about a final property of solutions, and that is osmosis. Osmosis is the flow of a solvent from a low concentration to a high concentration. And they could be separated by what's called a semi-permeable membrane, which means that it allows solvent to flow through, but it is not porous enough for the solutes to flow through. So if you've got something dissolved in water, the water can flow through, but whatever the solute is, it will remain on one side of that semi-permeable membrane. The amount of pressure that it takes to keep the osmotic flow from taking place is called osmotic pressure. So you have to have pressure pushing back with enough force so that that flow does not occur. And so it's pi, okay? And pi is directly proportional to the molarity of the solute particles. You're going to use R as a constant, just like we saw with the gas laws, 0.0821 or 0.08206 liter atmosphere over mole K. So the osmotic pressure is going to be equal to the molarity times R times the temperature in kelvins. So very simple. It's basically a plug and play once you get everything figured out here. So your osmotic pressure is going to be equal to molarity times R times T. So we have 5.87 milligrams of an unknown protein, and it's in 10 milliliters of solution, and it's at 2.45 torr, and it's at 25 degrees C, and you're wanting to find the molar mass of that. So if I'm looking for molar mass, then I'm going to rearrange, okay, to find that. So M is going to be equal to pi over RT. And this pi is a symbol, not 3.145, not the number, okay? All right, so we're going to then say that the pressure is 2.45 torr. And that needs to be in atmosphere, so I'm going to just go ahead and do that here. All right, and then that's going to give that number in torr. And then we're going to divide by R, 0.08206 liter atmosphere over mole K, times the temperature in Kelvin, which is 298, because it told us it was 25 degrees. All right, so that is going to give us this is molarity now, 1.32 times 10 to the minus 4 molar. So I can find how many moles I have because I know how many moles per liter I have. So I've got 10 milliliters, and this is in moles over liters. So I'm going to have to convert that to liters. All right, and then liters times the 1.32 times 10 to the minus 4 moles of the unknown protein per liter. And that's going to give me 1.32 times 10 to the minus 6 moles of the protein. So the molar mass, and remember it's like that, is going to be the grams of material. So we've got milligrams, so I'm just going to go ahead and see, that's milligrams times, there's in 1 gram, there's 1,000 milligrams, so that'll get us to grams. and then we're going to divide grams over the number of moles we have. 1.32 times 10 to the minus 6, because we're looking in, when we want the molar mass, that is going to be in grams per mole. So when I calculate that, I'm going to get 4.45 times 10 to the third grams per mole. And that doesn't surprise me, because proteins are very large molecules, so it makes sense that it would have a very large molar mass. And then in this one, it's more straightforward. You're just going to be figuring out the osmotic pressure using, which is what that symbol is, MRT. Okay? You have to figure out the molarity. You've got R and you've got T. So you should be able to do that without any problem. All right, and that is it. That was osmosis and osmotic.